Muhammad, and this is another video in the engineering mathematics series, and we are going to talk about the convolutional today. So I think that we are going to have an insight definition about the convolution and a couple of examples, and then we can see some visual example for it. So we are going to talk today about the convolutional theorem. Briefly, I'm not going to give it in detail because maybe the people in electrical engineering, they are highly interested in it and they can give more like details about it. But this is only a kind of general understanding of convolution and the convolutional theorem. Okay, let's go to the convolution and try to define it first and understand what is the meaning of its definition. So if we have two functions, which is f of t and g of t, are defined for t larger than 0, then the convolution, which is f asterisk g, okay, this is the what we call it the convolution, as we are going to explain it, what is the meaning of it, of the function f with the function g is the function defined by, this is the convolution here, with respect to a variable t, f asterisk g equals to an integration from 0 to t for the first function that we were talking about here, which is f. It should be f of t minus tau times the function, the second function, which is g of tau times d tau. Okay, so this is the integration that t larger than or equal to 0, such that this integral what converges. So this is the main definition for the convolution. So the convolution is all about an integration of two functions multiplied together, okay, for one condition that t should always larger than or equal to 0. In general, the transform of a product of functions does not equal the product of their transforms. Okay, that's a common thing, that whenever that the transform of the product of function does not equal to the product of their transforms. This is something common. However, how we can overcome this obstacle, however, the transform of a convolution is the product of the transforms of the individual functions. This is the main advantage of the convolution. The product of the transforms, okay, or the transform of the convolution is the product of the transforms of the individual functions. This fact is called convolution theorem, okay, and is the rationale for the definition. So all of this is related to this convolutional theorem, that we have like two functions. The transform product of these two functions does not equal, they are not the transform, Laplace transform of the product of these two functions does not equal to the product of the Laplace transform of the individual function. So if we are going to provide another tool, which is convolution, we found that if we could obtain this integration with this limitation, that t larger than 0, and we can put our two functions in this form, and the integration is going to converge, then in this case we can use the convolution and we can get the product of the transforms of the individual function, as we are going to see in the next slides. Okay, now let's go to the theorem itself, the convolution theorem. So the convolution theorem is Laplace transform of f asterisk g, this is one function and this is another function, okay, which is the convolution, okay, equals to the Laplace transform of the first function times the Laplace transform of the second function. Okay, so now we can multiply them because this is a convolution, the transform of the convolution. Okay, so this f asterisk g, this is convolution. Okay, it's not multiplication here, it is convolution. This is how we can give definition for the convolution. Okay, f asterisk g means the convolution of f and g together. So Laplace transform of this convolution equals to the multiplication of Laplace transform of each one. Equivalently, we can say that Laplace transform of the convolutional with respect to the s parameter equals to f of s times g of s in a capital form. Okay, so that's our main idea here. A proof is outlined in problem 26. If you want, you can go and do it by yourself. It's only for your information. Okay. The inverse transform version of the convolution theorem is, this is the inverse Laplace transform of the convolution fg between parentheses or braces like this. The inverse of it is going to be f asterisk g. So this is the convolution. What is this? It is the Laplace transform of the function f, and this is the Laplace transform of the function g. Okay, so this is very nice because we are going to overcome the obstacle that we have outlined here, that the transform of the product of functions does not equal to the product of their transforms. However, the convolution could solve this for us. As you can see, it has been solved. Now f of s times g of s transforms, they are the individual transforms, production here, multiplication equals to what? Laplace transform of what? The convolution. And inversely, we can obtain the inverse of Laplace transform of the convolution. Then it is going to be this is the convolution, the inverse transform of the Laplace transform of the product of the individual functions would give us the convolution. Okay? This states that the inverse transform of a product of two functions, f of s and g of s, is the convolution f of g. That's right. Of the inverse transforms of the functions. That's very true. Okay. This fact is sometimes useful in computing an inverse transform. So when it will help us in computing an inverse transform. Computing an inverse transform. Okay. Now let's take an example and see how we can solve this. Okay. Now compute this inverse transform of this function, 1 over s times s minus 4 to the power 2. Certainly we can do this by the partial fraction decomposition as we have learned in the previous video. But we are going to work it with the convolutional theorem. Okay? So we are going to assume that we have two functions that is multiplied here, and they are as if they are like Laplace transform. Look here, we can say that this is like 1 over s times 1 over s minus 4 to the power 2, right? This would be here. So you can tell that this is like something from the table, and this is also, we can find it from the table. I mean Laplace transform table, right? This is exactly what we want. We want to make whatever inside these braces to be like Laplace transforms. So we are going to do it. We are going to say that the first function, it is going to be 1 over s, and the second function, which is g of s, it equals to 1 over s minus 4 to the power 2. Take care, it is capital form. This means that we're talking about Laplace transform. So we are computing the inverse transform of a product. Now, this is the inverse transform of the product of two functions, f of s times g of s, right? So this means that it equals to what? Exactly, it equals to the convolution. So by the convolutional theorem, okay, that we have explained in the previous slide, the inverse transform of the the multiplication of two functions, which is f of s and g of s, it would equal to the convolution, right? Well, now let's go and see what is the continuation of this. Now we are going to say that our function, the first function, which is 1 over s, we want the inverse of this function, because again it is inside this inverse of transform, right? So the first one here is L, or the inverse transform of 1 over s. From the table we can get it easily, 1. And the second function, which is 1 over s minus 4 squared here, which is, we're going to call it g of t. Take care, here it was f of t, which is small letter, and g of t, which is small letter. Then the inverse of 1 over s minus 4 squared. This is very easy. Also, you can obtain it from the table, right? From the table, entry number 4, you can find t to the power n e to at. It would equal to the factorial of n over s minus a to the power n plus 1. Okay, so from the table you can obtain this inverse transform here easily for the two functions f of t and g of t. Then our inverse of this between the braces, our main problem, is going to equal what? F of t asterisk g of t. Take care, asterisk does not mean product here. It means convolution. F of t convolution g of t. Okay, that's the definition here. Okay, so based on this, we are going to say that the inverse transform here is going to be equal to 1 times this value of f of t. Okay, the transform here, okay, 1, the inverse 1, and t times e to the power 4t, which is 1 convolutional t e to 4t. This is, again, as I said, this is convolutional. It does not mean multiply. It does not equal to 1 times t e to the power 4t. No, it is 1 convolutional t e to the power 4t. So what is the definition of the convolutional or the convolution? It is the integration of from 0 to t for tau times e to the 4t d tau. Sorry, this is, we are talking about tau here. So the limits are going to be from 0 to t. Okay, now this is very simple kind of integration by parts. We can integrate it, okay, and we can get these values, okay, for the last output of our inverse. So the inverse or Laplace transform inverse for this function is going to be easily computed, as you can see, with these 3 terms. Okay, remember, what I want you to remember is this. Okay, remember that, and remember that this is 1 convolutional t e to the power 4t. Let's go to the definition again. Remember that this is the definition here, that the convolution of f convolution g means that the integration from 0 to t for the first function, which is f with t minus tau, times the second function, which is g of tau d tau, and our limited integration from 0 to t. Okay, the limits of the integration. So this is what we have done here. This is our integration 0 to t, and then we put tau times e to the 4t here, and then we integrate and using integration by parts, and we could obtain the value. Okay. There is one characteristic for the convolution, is it is commutative, means that f convolution g equals to g convolution f. This can be proved by a straightforward change of variables in the integral defining the convolution. You can do it, but no need to make it. Just you can change the variables here. Okay, instead of f of t minus tau times g tau, make it like g of t minus tau times f of tau. If you do this, you are going to find easily that convolution is commutative. Okay, in addition to its use in computing the inverse transform of products, convolution allows us to solve certain general initial value problems. So certain initial value problem also can be solved by the convolution. Let's have this example, which is example 3.15 in the book. Before going into the details, I want you to remember what I have explained in the previous video before, that the Laplace transform of the first derivative equals to s times Laplace transform minus f evaluated at 0, and Laplace transform of the second derivative of the function equals to s squared f of s Laplace transform of the function minus s times f evaluated at 0 minus f prime evaluated at 0. Okay, this is two important equations. We're going to use it in this example. Now we want to solve this initial value problem, which is y double prime minus 2y prime minus 8y equal to f of t. Take care that in the right hand side there is a function called f of t. And we have an initial value problem, so we have some initial conditions: y of 0 equal to 1, y prime of 0 equal to 0. Okay, so we want a formula for the solution. The solution here means what? It means that y, okay, y of t, for example, this is the solution for our differential equation. It is different than the forcing function, which is in the right hand side. So the solution means that y of t, okay, that will hold for any reasonable forcing function f. So apply the Laplace transform to the differential equation in the usual way. So we are going to take Laplace transform of the two sides of the equation and see what will happen. So Laplace transform for the second derivative, so remember it will be from this equation. So for the second derivative, Laplace transform is going to be something related to this, okay, which is the first part, and then the second term, it is 2y prime. Take care, y prime, it is going to be s f of s minus f0. So this is the second term, and 2 here, this is the first term, and then minus 8y, it is going to be minus 8 capital. We are talking about Laplace transform now, so everything is going to be changed to Laplace transform, y of s, y of s, y of s in a capital form, in an uppercase. It equals to the right hand side, which is Laplace transform of the forcing function. It is going to be f capital of s. Okay, so now we are going to rearrange this equation, the right hand side and the left hand side, and when we rearrange it, we found that if we put y of s in the left hand side, we're going to left with two terms in the right hand side, s minus 2 over s squared minus 2s minus 8 in the denominator, plus another term which is having the same denominator here, and there is numerator 1 times f of s. Remember that f of s is going to be always there because it is in the right hand side, the forcing function, Laplace transform of the forcing function. Okay, now let's factor this denominator. It is going to be s squared minus 2s minus 8. It is going to be s minus 4 times s plus 2. It is going to give exactly the value here. And use partial fraction decomposition. And you know well now what is the meaning of partial fraction decomposition. If you do not know, stop this video and go to the previous video, and you will understand it clearly, because I have given a detailed example about partial fraction decomposition. Then we are going to rewrite it again. So we have here like these two terms in the denominator. This means that we are going to have, for each term here, we will have two terms. This is the first term and this is the second term. And for the second term here, we're going to have two terms, 1, 2. And here, because it is multiplied by f of s, so we will have f of s presented here always. So from where we got 1 over 3, 2 over 3, 1 over 6, 1 over 6, please revisit the previous video and you are going to understand how we can obtain these constants. Okay? It is easy, but you need to go through the example as I have explained in the previous video. Now we can apply the inverse transform to obtain the solution. We're going to apply the inverse transform. Okay? So inverse transform of y of s is going to be exactly y of t, right? And all of these function, it is 1 over s minus 4. This means that from the table, remember that e to the power at from the table equals to 1 over s minus a. So here 1 over s minus 4, this is going to give us e to 4t, and this is s plus 2, so it is e to minus 2t. Here s minus 4, e to 4t, and then here 1 over s over 2, so it is e to minus 2t. Okay? Now this is very easy from the table, you can obtain it, which is valid for any function f. This means what? That our solution for the differential equation that we have here is going to be equal to all of these exponential functions times our forcing function. This is the solution of our differential equation. This is the solution of our differential equation. Okay. Now I'm going to give some like visual examples, means that only to understand. I'm going to revisit again the main idea of convolution because I know that maybe it's a little bit vague and not clear. What is the meaning of convolution for us? What is the meaning that whenever we say that G, okay, convolutional of f, what does it mean physically? Okay, I'm going to explain about this issue in the next slides briefly. Okay, so I'm going to give this visual example. You can visit this website. You're going to find some visual examples for it. So actually the main thing for the convolution, the main definition in mathematics, in particular functional analysis, convolution is a mathematical operation on two functions. Okay, we're talking about two functions here, f and g, to produce a third function that expresses how the shape, look here, how the shape of one is modified by the other. That's very important. If you have a function like this and another function like this, if they are going to multiply and they are moving, how they are going to be changed, how one of them is going to be changed. Okay? The term convolution refers to both the result function and to the process of computing it. So this is the meaning of convolution here. Okay? This is like physical understanding of the convolution. Okay, here there is some wording. I do not want to go into the details of it, but just I'm going to read it for you to understand the idea. Convolution has to do with the multiplication of transforms. So this is the main idea. Convolution is related to the multiplication of transforms. The situation is as follows. Addition of transforms provide no problem, which is the linearity of Laplace transform, right? We know that Laplace transform of f plus g equal to Laplace transform of f plus Laplace transform of g. This is common sense and we have studied it before. Now the problem is in the multiplication of the transform, which is occurring frequently in connection with ordinary differential equation, integral equations, and elsewhere. So multiplication of transform is commonly repeated in our problem. So we need to find a way to solve it. Then we usually know that Laplace transform of f and Laplace transform of g, and would like to know the function whose transform is the product. We want to get the product here. What is the function for the product of them? Okay, from here the convolution idea came across. Okay, so we might perhaps guess that is f times g, okay, is going to be the product of the two functions, but this is false. I mean that this is not right. The transform of the multiplication of two functions would not be the product of them. The transform of a product is generally different from the product of the transforms of factors. This means that transform of f times g does not equal to transform of f times transform of g. Okay, take care here. Look, it is fg. It is fg directly. It is not f asterisk g, because this is the convolution. Okay, we are not talking now about this. Just we want to say that the multiplication, the transform of fg, does not equal to the transform of f times the transform of g. From here we came across, or we have explained what is the meaning of the convolution, right? So we said that the f convolutional g equals to this kind of integration, okay, as we have explained before. Okay, now I want to show you this. Sorry, I'm not sure why it doesn't work. I think that because it is not. Let me check here. Okay, there is some visualization here, but I'm not sure actually why it doesn't work. So maybe there is something wrong that happened. Okay, so actually this should be like something moving here, and you are going to find that this function is going to be changed. So I'm sorry for this, but I think that there is some problem. This is not working. But anyway, you can see if we go back. Okay, I strongly recommend for you to go to this website, and you are going to see the this visual example of the convolution. Okay, I'm not sure why actually it doesn't work here. So you can visit the website that I said to you, and here there should be another function that is going to move here, and then there is in a movie you are going to find that the yellow is going to be the convolution of each one. So again, you can visit the page that I have said to you, I expressed or that I have mentioned before, and you are going to find this visual explanation. Now let's go to the in-class assignment. Now use the convolution theorem to help compute the inverse Laplace transform of the function. This is our function here. I think it's pretty easy for you. You can think always, if you want to get the Laplace inverse transform of this, then think about it as one function here and another function here. Okay? So if you are going to make this as in-class assignment, please stop the video here and try to solve it by yourself. Okay? Solve it by yourself before looking to the answer that I'm going to show to you here. Okay. Now let's go. This is the answer actually for it. So we are going to have, as we said, two functions, 1 over s squared plus 4, and another function which is s squared minus 4. This is, as we said, this one here and another one here. Okay, then we are going to take the Laplace transform, the inverse of Laplace transform of the first one. This is 1 over s squared plus 4. Laplace, the inverse of it is going to be half sine 2t. From where? This is, you can obtain it, get it from the table entry 6, and using this is from the table, this entry, you can get this 1 over s squared plus 4 half times sine 2t. And Laplace transform the inverse of g of s, which is the second function here, it is going to be sine 2t, half times sine 2t. You can visit also the table and you can obtain this value easily. By the convolution theorem, we are going to say that the inverse of these two functions is going to be, as we put it here, it is going to be 4 sine 2t convolution sine 2t. Okay, because we have half here and we have another half here, so it is quarter here, 1 over 4. And then sine 2t convolution sine 2t. Okay, then we are going to put the integration here, which is 1 over 4, it's a constant, and then we have the integration from 0 to t. This is the convolution interpretation, sine 2 t minus tau sine 2 tau d tau. As we said, this is the definition of the convolution. Then you can make the integration by parts, and you can follow this exactly. We're going to find cosine comes here, sine, cosine, and cosine sine here from 0 to t. This is the limitation or the limits of the integration, and you can end up with sine 2t minus sine 2t. Okay, so this is involve a lot of kind of integration by parts. You can do it by yourself. If you are interested, I solve it for you here, so you can check it in detail. As you can see, it goes in detail here. You can go through it, and you will find at the end the results as we have explained before. Okay, so this is the in-class assignment. I hope that you work it by yourself well. Now let's go to the home assignment for today, and please, this is the home assignment using the convolutional or the initial value problem. You can solve these two equations. This is 1 and 2, y double prime minus 5y prime plus 6y equal to f of t. It is very similar to the example that we have done before, and this one similar also, but here also f of t, and we have the initial value problem here. So please solve it and get the final solution in terms of f of t. Very similar to what we have explained. If we go back here, it is very similar to what we have explained, I think, here. Very similar to it. So you are going to get trained well on initial value problem using our definition. Okay, so this is for today, and thank you very much for watching, and I hope that you can understand convolution. As I said, it is only a kind of like just understanding some definitions and basic idea about convolution. It's not in detail, and you are not required or requested to know much more about convolution. Just understand what I have explained here, and this is going to give you the basic idea. Thank you, and see you in the next video.